Okay, so in this video we're going to look at linear sequences, and another word for linear sequences is arithmetic sequences or arithmetic progressions. So in brackets I've written APs here. But what we're going to see is that these are closely related to the functions and equations that we've been looking at so far. Okay, so let's start with an arithmetic progression or linear sequence. And we'll keep it nice and simple. Let's start with something like this. So 3, 7, 11, you probably see where I'm going with this, 15, and let's just stop there and say, well, that goes on forever. Now what we can do immediately is plot this on a graph. So I'm going to just draw some axes over here, and the way to plot this is slightly different to the normal x-y axes that we have, and I'll show you what I mean. If we say along here we're going to have, well, conventionally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then what we've got this is here is the number of the terms. So the first term is represented by 1. So 3 is the first term, so the first term is 1, and if we go 1, 2, 3, then we can plot it on our axes like this. Okay, so what have we got here? We've got, we could label this x, but we're actually counting the number of times, we're counting the number of terms that we've got. So we tend to call this n, so we'll give this the label n axis instead of x. Now up here we've got the values, so let's just complete the numbering. 7, 8, 9, 10. Did we get this right? No, we missed out a 5. I am sorry. Okay, let's just rub those out. Okay, like that, and put that in properly. So 5, 6, 7, 8, 9. Now we could call this y. 10, there we go. But we tend to actually call it u. It doesn't really matter, but u is the conventional notation for the value of any term in a sequence. Anyway, let's get back to that sequence and see what we know about it. Well, the first thing we know about is that the first term is, let's put that here, the first term, we'll call it a, is 3. So what's special about a sequence as opposed to a normal, a conventional function, is that it starts at n equals 1 and it doesn't go any lower. So we're not going to find any of our terms or values going further down here. We're only going to see them going along 1, 2, 3, 4, 5. And we're also not going to see anything in between 1 and 2 or between 2 and 3, because there would be no such thing as a sort of 1.5 term. So what we're going to get is not a line, but instead a series or a sequence of dots on our graph. Okay, the other thing we know is that we have a common difference between each of our terms, and that common difference, as you can see, is +4. So each time we jump from one term to the next, we add 4. Add 4. So that common difference between the terms we'll call d. d equals 4. Okay, let's plot the other 3 terms then. So our second term, so n equals 2. Our second term is 7, so up here. Our third term is 11, so that would be here. And our fourth term, 15, we can't fit on the graph. But you can see what's going on, and you can see why these are called linear sequences, because what we've got is a series of dots progressing in a straight line from n equals 1 and u equals 3 up here to 2, 7, and then 3, 11, and so on and so forth. So that's those are our coordinates, and this gives us the idea that I'm going to work with next, which is, can we find out what the function is that produces these dots? Well, we ought to be able to, because we know that the first term of a function, and we'll call this then f of n, the function of n. The first term, the coefficient of n, as we've seen in previous videos, is the gradient of the line. Now, we haven't got a line in this case, but we have got, if you like, a sort of invisible line. And we get the gradient by dividing the rise over the run, as we used to call it. In other words, this distance here divided by this distance here gives us the gradient of the whole line. Now, this distance here is always, with any sequence, of course, going to be 1. Okay? So that distance there is going to be 1. So we don't need to worry about it, because if we're dividing by the run here, this distance along the n-axis, then we're dividing by 1, and that means the value will stay the same, because 1 is the identity for multiplication and division. So all we need to worry about is this vertical distance here, the distance on the u-axis, and that's going to be the common difference. Okay? It's the difference between, in this case, 7 and 3, so 4, which is our common difference of 4. So the coefficient of n in our function is simply going to be 4. And now what we need to do is we need to fill in the constant term in our function. And that, as we've also learnt in previous videos, is going to be the u-intercept. Usually we say the y-intercept, but in this case the u-intercept. So it's going to be, if you like, the 0 term. So it's when we extend this line backwards, and it would intercept the u-axis here. Let's put our negative numbering in, -1, -2, -3. So it would intercept at -1, as we can see, and so our final term, constant term, must be -1. Okay? Now, another way of thinking about this would be, if we didn't want to do a graph, for example, would be, well, what if our first term was just 4n? So if our first term, n equals 1, was just 4n, then 4 times 1, it would bring it up to here. Okay, let's use a different colour just to make things very clear. So our first term would come up to here, and to get from here to here, we would have to subtract 1. So 4n minus 1 must be the function. Now, a couple of things just to modify here. Let's just erase that for the moment and erase these. We don't generally use this terminology for the function of n. So instead we're going to say, well, what is the function of n? It's the value u for any number of terms. So we say either, there we go, let's get back there. So either we say u sub n, or we might just say the term-to-term rule, or the nth term. But the function, anyway, is 4n minus 1. That's the important bit. Okay, now this gives us a way of calculating then any term for in the sequence. So say, for example, we wanted to know the 10th term, then we would say, well, u sub 10, the 10th term, must equal 4 times 10, because it's the 10th term. So 4 times 10, subtract 1. And that equals 4 times 10 is 40, minus 1 equals 39. So the function tells us, if we use it, if we plug in our values, that the 10th term, or any term we can calculate, but in this case the 10th term must be 39, and that looks about plausible. If I go over to n equals 10 here, if I was to project upwards, I can quite believe that that would be the u value would be 39. Okay, let's try another one. So we'll call this A, and now we'll go for, let's go for a descending sequence. So what should we try? Let's just try something fairly simple. Let's try 13, 10, 7, ... Okay, so you can see where I'm going with this. So D in this case is minus 3 because we're descending in the sequence. And if we plot this on our graph, let's use a different color. We would start with 13. Well, we can't fit that on our graph, but if we look at 10, that would be the second term, so 10 would be plotted here. Now if we put the 7 on, that would be our third term. We can see very clearly that our fourth term would be u equals 4. Our fifth term would be u equals 1. Our sixth term would be u equals minus 2 then, because I'm going down 3 each time, and so on. Okay, and we'll stop there. So that's plotted it on our graph, and now we'll try and find the, well, before we do that, let's just write a equals 13. So our first term in this sequence is 13. Good. Okay, now what's our function? So our nth term would be minus 3, because the common difference has got to be our coefficient of n. And if the first term was minus 3 n, and n was 1, then minus 3 would be down here. So let's indicate that down here. So minus 3 times 1 would be down here. So the graph is quite a useful visual way of saying, well, what would we need to get up to, sorry, let's just think, what would we need to get up to 13? Well, 13 is up here. So I just got a bit lost there, because of course 13 is off the graph. But if we just write it in pencil up here, then we've got to find the difference between this and this. So to get from here up to 13, we would need to add 16. Okay? So our intercept must be plus 16. And does that look plausible? Yeah, if this was to go up, it should intercept at 16. So that does look like it's correct. Must be correct. So that's just a little visual check. Okay. All right. Let's now think of the, well, let's think of the 10th term again. Where would the 10th term be? So if we write u sub 10 would be minus 3 times 10, because n equals 10 this time, plus 16, our u-intercept. Okay, well, in this case, we've got minus 30 plus 16. I'm going to write 16 minus 30, just commute it. And 16 minus 30 is going to be minus 14. So, in other words, our 10th term, where n equals 10 here, would go down and down if we were to plot it off the graph at minus 14. Does that look like it would line up? Yes, it does. And so that's going to be correct. Okay, now what I'm going to do here is erase what we've done so far and think now about a real world problem. Because very often these sequence problems are expressed in word form. And what I'll do is bring up a real person then. So here we've got Paula, and Paula is going to run a marathon. So let's write C. So to run the marathon, Paula is going to practice. So she's going to build up slowly. She's going to start with, let's say, 5-mile run. So the first term is going to be 5, so we can mark it on our graph here. Let's use a different colour actually. So let's use red. Okay, there we go. So her first run, 5 miles. Okay, like that. Okay, so that's plotted it on the graph. Let's keep on the graph and just see what happens next. So if she adds, let's say, 1.5 miles every day, so on her second day, what's she going to be doing? She's going to be doing 6.5 miles. So we should write miles as a label for our u-axis now. In the third day then she's going to be running 1.5 miles more, so that will be 8 miles. And the fourth day she'll be running 9.5 miles. So let's write down those values. So we have 5, add 1.5 will give us 6.5. The next term has got to be 8, then 9.5, and then we just say dot dot dot. So our common difference is 1.5. And our first term that we're calling A is 5. Okay? So what are we going to want to find out about Paula? Well, there's various things we could ask. We could ask how long does it take before she runs a full marathon. Let's keep it simple. Let's just say, well, how many miles is she going to run in the 10th week? So in this week here, 10th week, how many miles will Paula run? So again, we need our nth term rule, or term to term rule. So we have a coefficient of 1.5. Let's call that 3 over 2n. And our intercept, well, we can read this off the graph because we're going to subtract 1.5, so our intercept must be here at 3.5. So this is plus 3.5. Or we could say, well, there's various ways of doing it. If we say our first term would be 3 halves, how far do we need to go up from 3 halves to 5? Well, that would be 3.5. Okay, so 3 halves, 1.5, gives us 3.5 to get to 5. So however you want to calculate it, there are different ways of thinking about that. It should be fairly straightforward to arrive at this function. So now that we've got our function, we want to know what Paula does in her 10th week. So our 10th week is represented by u sub 10. Now we have our formula, or our function if you like. 3 over 2 times n is 10, so it's 30 over 2. Plus 3.5, which is 7 over 2. Gives us 37 over 2, which is, well, half of 30 is 15, and half of 7 is 3.5, so 18.5 miles. So, by the 10th week, Paula has got up to 18.5 miles, so she's still got a way to go in her training. Okay, let's try another problem. And this time, I think what I'll do, well, let's bring our problem up first of all. So here we've got Greg, and Greg is going to lose weight. So now let's just write this out, I think, so that we can see what we're doing. So if we write D, let's start Greg at 100 kilograms. Okay, so that's his weight to start with. And let's have Greg losing 1.2 kilograms every week. So in that case, our common difference is going to be minus 1.2, and our first term obviously is 100. Okay, so that's set up the problem. Now there's one other thing that we need to do before we start working on this, which is we'll need to change the numbering on the axes. So let's just erase these, and let's erase Paula's miles as well. And the reason why we're going to have to do this, and we'll have to erase these as well, is because what we're going to do is bunch these values up. I'll show you what I mean. So, if we start here, we know that our line of dots is going to descend, but if we start at 100, we want it to go down and down like this. So I think what I'll do is if I subtract 2 each time, so I'll end up with 98, 96, 94, 92, 90, 88, 86, 84, 82. Now when I come to here, obviously this is 0 here and here, so I need to do something a bit clever here. I'm going to just rub out this line here and put in a little squiggly line, so it's as if I've introduced a little bit of elastic, so like that. Okay, and that means I don't have to redraw my n-axis as well. Okay, let's just erase this arrow here as well. Okay, so we've set up a problem. We're ready to find the solution. What do we want to find? Let's say that Greg asks us, when will I weigh less than 89 kilograms? You know, after how many weeks will I weigh less than 89 kilograms? Okay, well, let's find out. Now, first of all, let's plot our sequence on the graph. So each time we're going down by 1.2, so the next one's going to be 98.8. Okay, then we've got 97.6, and that will do for the moment. We'll just go dot, dot, dot. Okay, let's just change color. Let's have, I don't know, let's have purple this time. Okay, so we have our first term, which is 100, so we mark our 100 here. Okay, 98.8 is our second, so after 1 week in our week 2, we've got 98.8, so that's going to be here. I just need to be a little bit careful here. I often get confused, and it's very easy to get confused. This is, if you like, our 0th week, week 1. So after 1 week, this is our, here is our first week. So at the end of our first week, it's going to be n equals 2. So I just mark that in because it tends to get a bit confusing. Our 10th, n equals 10 here, for example, is going to be our 9th week. So just worth marking that in so we don't get confused. All right, let's mark in the other values that we've got. We've just got one more, so 97. So n equals 3. 97.6 is going to be about there. Okay, and we can see our line progressing now. Okay, maybe we should mark in just one more so we can see it more clearly. So our next value would be 96.4. So 96.4 would be about there. Now we can see our line fairly clearly. Okay, let's now go for our nth term then, our nth rule. So u sub n equals minus 1.2, let's say minus 6/5, because that's a bit more conventional. Doesn't matter if you write 1.2 n, but 6/5 seems a bit neater, so 6/5 n. And what's going to be our intercept? Well, we can see that very clearly. It's going to intercept about here, and that's when we add 1.2 to 100, so we're going to have 100 and 1.2. Okay? Now, all that remains is to give an answer to Greg's question. Greg has asked us, when's he going to weigh less than 89 kilograms? Well, let's have a guess that when n equals 10, in other words, in our 9th week, week 10 is our 9th week, then we're going to have, well, what are we going to have? We're going to have minus 6/5 n, which will be minus 6/5 times 10, so minus 60 divided by 5 plus 102. Sorry, 101.2. There we go. Now, fairly straightforward, but I think it would be helpful if I just reverse this. So I'm just going to commute these two terms so that I get 101.2 minus, well, 60 over 5 is going to be 12. Okay, so let's work this out. If I, let's subtract 11 from both the 101.2 and the 12, because that will make life a little bit simpler. So that's going to be 90.2 subtract 1, which will give me 89.2 kilograms. So what we can say to Greg is that, well, after in your 9th week, in other words, week 10, you are still going to be over 89 kilograms, I'm afraid. But in your 10th week, which we can call week 10, then you will indeed be under 89. You'll definitely be under, if all goes to plan, you will definitely be under 89 kilograms. Okay. Okay, let's look at this formula. Now, this is the formula that very often students are asked to memorize when dealing with, and to use when dealing with arithmetic progressions or linear sequences. Instead of that, what I've shown you in the first part of this video is how to think about it visually and to understand what's going on. But if you do like understanding and using formulae, well, then here's a very useful one. So what have we got here? Well, the very first thing that we tend to want to go for, as we've seen in the video, is our values for a and d. So here we've got our first term, so u1, let's call it u1, and we called it a. Okay, our first term is a, and so our second term, u2, u sub 2, will obviously be a plus the common difference, so a plus d. u3 then, what will u3 be? Well, it will be a plus d plus another d. In other words, it will be a plus 2d. u4, u sub 4, will be a plus d plus d plus d. In other words, 3d. And let's do one more. u5 will be a, whoops, let's just get that right. u5 will be a, u sub 5 will be a plus d plus d plus d plus d. In other words, plus 4d. Now, what's going on here is, again, this problem with numbers not exactly matching up, and that's where this n minus 1 comes, because if we look at the second term here, where n is 2, then okay, we've only got 1 times d. But with the third term, when n is 3, we've got 2 times d, which is n minus 1. Again, here, when when we do with the fourth term and n is 4, then we've got 3 times d, so that'd be n minus 1 times d. So it's always n minus 1, which is where we get this rule here, n minus 1 times d. So that's where it comes from, and it's a very straightforward thing to use, a straightforward thing to understand. But if you're going to memorize formulae, be careful, because if you try and memorize too many formulae, you can easily get confused. Understand where it comes from, and then perhaps it's easier to remember and use. Now the other thing that I'd like to point out just before we finish this video is this that we were using in the first part. So what this says is that u, when n is 0, so if we like the 0 term, or the 0th term, well of course there isn't a 0 term because the first term is the first term. But if there were a first term, as we've seen visually, we can draw that back to u0, and so the 0 term must equal a, this time subtract d. So a subtract d gives us our 0 term, and that can be a useful concept to work with. And it leads to this formula, which again, if you like formulae, you might want to remember, which is again a rule for finding the nth term. So we've got a function again, and this is the function that we were working with in the video. So here we have the gradient of the line, and we have that's the coefficient of n, and here we have our 0 term. So a subtract d gives us our 0 term, which is what we've been calling the u-intercept on the graph. So I don't know whether you like formulae, I don't know whether you want to or need to memorize things. It's better if you can work things out, but sometimes remembering formulae can be very useful. It certainly speeds things up, and sometimes you can be required to remember these things. So there they are.